Well, our next talk is entitled Building a Personalized Voice Assistant for Music, and it's going to be given by Isaac Julien. Isaac is a research engineer at BOSE, where he prototypes machine learning enabled experiences for future wearable products. So I'll take it from here, Isaac.
Thank you. And is my slide visible? Okay, great. So hi, everyone. My name is Isaac, and I'm a machine learning engineer on the BOSE Applied Research team. First of all, thanks to the organizers and for the invite. I appreciate the opportunity to talk about this work. And today I wanted to talk about a project I worked on when I first joined BOSE in 2017. And at that time, I was part of a small, relatively new group of machine learning and NLP engineers working on designing and prototyping experiences that might complement our products a couple years out in the future. Well, one of these early experiences was the BOSE Music Assistant. And I should mention that we've since stopped work in this area. The project culminated in a prototype that was used and enjoyed internally, but ultimately did not fit into business plans. And my team has since moved on to working on other machine learning applications. So you won't see this project come into any of our products, but we did want to share how we designed an NLU system that was practical for our purposes, and some of the interesting NLP challenges we encountered in the music domain, and also the opportunity that these challenges provided for us to give a more personalized experience. So the BOSE Music Assistant was a year-long exploratory research project with a small team to build a voice interface focused on a single domain, music. And our goal was to make it easier for people to find and discover music that they really enjoy, to supplement the experience of listening on high quality headphones and speakers. And this was intended to live alongside other general purpose VPAs, not to replace them, and to enhance the experience within that single domain of music. Two features that were important to us were personalization and dialogue. Personalization meaning that as you use the system, it's able to learn your preferences and use that in some beneficial way. And dialogue we saw as an important tool to help someone explore or narrow down what they wanted to listen to without having to know everything ahead of time. So here's a sample dialogue that emphasizes both of these ideas. And one of the core pieces we wanted to own was the NLU, so that we could control how what the customer says is interpreted. In contrast, for example, we opted to use an existing ASR rather than build our own, but we wanted to own the SLU or NLU part of the system. And two of the important tasks here are intent classification and slot filling. As a reminder, for intent classification, we want to figure out here that the intent is to play music. And for slot filling, we'd like to know that there is a song called Old Days and a location called Living Room. And the main challenges we faced were first being able to handle the variety and ambiguity of natural speech, and to be able to add to the system's understanding quickly in the form of new intents and slots. And second, incorporating domain knowledge here from music. And of course, everything has to run fast enough so that the end-to-end experience feels natural. Our solution was a hybrid system that combined a grammar-based parser with a machine learning component. On the left, you'll see a toy grammar in our custom format that we designed for this. And it's designed to be easy to read and write for a non-NLP expert. As you can see, it includes non-terminals that can be expanded, optional symbols, various ways to combine these, as well as features that aren't shown here, such as wildcards and placeholders for entities like songs and artists. These grammars are defined in text files and then compiled using our own ANTLR-based parser. And on the right is the machine learning model that complements the CFG parser. We used a BiLSTM on top of glove embeddings to jointly predict intent as well as per token predictions for slots using IOB format. We also experimented with BERT-based models and saw a large improvement of accuracy there, although at the cost of some latency. The main benefit of the CFG parser was that it allowed us to quickly prototype new intents, which was particularly important with any multi-turn dialogue flows that we considered. Meanwhile, we could pass anything that didn't match the grammar to the ML side, which provided a more robust experience, since even with features like wildcard, it's difficult to capture a reasonable portion of what people might say. The role-based component was also important to quickly get the functionality to a point where people could use it comfortably, internally at least, allowing us to collect more realistic data with which to train the ML model. And it also let us maintain a large set of common inputs so that we knew whatever happened on the ML side, that the most common inputs would be handled correctly and quickly in the grammar. And finally, we were also able to use the grammars to actually generate some synthetic training data for the ML model to supplement the real data we collected, and found this to be beneficial, especially for bootstrapping new intents. So after parsing, we ended up with potentially multiple intent and slot hypotheses. And the next step was to link each entity to a music knowledge base and re-rank the parses accordingly, which is done in what we call the ISM, or Information State Manager. And as a side note, this knowledge base also provided candidates to fill in any placeholders in the grammar, which was done by augmenting the grammar rules at parse time. So as an example for entity linking, in this case, we want to connect the track Old Days to a specific entity in a knowledge base, which may provide information important to understanding and fulfilling the request. And we found that this task presented some unique challenges when dealing with music entities like tracks, albums, and artists. The first challenge we encountered, which I'll show some examples of in a second, is that music is a creative endeavor. So a lot of tracks, albums, and artists have creative names. And the second was that there's a really high level of ambiguity. So here are a few examples of some creative song and artist names, which are often challenging for the ASR and therefore hard to match to the knowledge base. Deadmau5 and Boyz II Men are different groups with creatively spelled names. Skater Boy, my favorite song from growing up. And then I think the last one is an Ed Sheeran album that's just named the plus symbol. And in our system, this basically had the effect of increasing the number of possible matches and therefore possible parses we had to consider. And along with this, the second challenge was ambiguity from overlap between song, album, and artist names. For example, there's a popular band named The Weeknd, stylized without an E, but there's another less popular band called The Weeknd with the correct spelling. But if we naively matched ASR output to this band, it would probably be the wrong choice. Here's another example that I personally find really amusing. These are all unique tracks in the knowledge base. And the fifth one down is by Michael Jackson, and is probably the one that we want if someone asks for it. And as a result of this high level of ambiguity, for many phrases, there are probably multiple substrings that might match multiple types of music entities. For example, here are some ways you could interpret Play Some Blues. The meaning's clear to us, but without additional information, the NLE needs to consider that blues is also the name of not one, but multiple albums, and also some blues matches multiple tracks and multiple albums. And at one point, we plotted out the overlap between names in our knowledge base, and it was surprisingly high. The way to read this is that, let's say, 44% of tracks in the knowledge base have a name that also matches an album name. So a lot of songs share names with another song, album, or artist. Fortunately, we were able to largely solve this problem using listening data collected from BOSE devices out in the real world. And for this data set, other metadata was available to help us easily link each track someone played to an entity in the knowledge base. Using this, we were able to generate a popularity score for each unique track. So in the sample data, we see two different tracks named Rockstar, but since one of them has been played 3 times and the other only once, we would choose the first, given only the name. And we chose to keep a rolling popularity score to account for changes in song popularity over time and to handle new songs. But we can go further. And this challenge was one of the areas we saw as an opportunity for personalization. Here we have two songs with the same name, the one that got away by Katy Perry, and who's a pop artist, and then by Jake Owen, who is a country music artist. So two people could ask to hear this song and say the same name, but expect different results. And looking at our data set, both of these are pretty similar in popularity. The Katy Perry version is a little more popular. So if we know nothing about a user, we should probably play that version. But if we know they really like country music, maybe the Jake Owen version is a better bet. So we wondered how much of a problem or opportunity is this, and sampled about 13,000 songs from 500 users to ask the question, how often did someone choose to play a song that has another popular song, another more popular song with the same name, as a proxy for when matching the most popular song mentioned in a natural language query would be wrong. And we found that happens surprisingly often in this data set, around 20% of the time. To address this, we sought to combine the overall popularity of the tracks, albums, and artists in the knowledge base with some measure of how a specific user's musical taste relates to each track. And we did this by treating the overall popularity score as a prior probability of the correct track, and then building models that would estimate the probability of a user given each possible correct entity matched in ASR, so that we could combine them as follows. And the way we built these models was to sample a small number of other random users and train a model to predict the true user given the track, and then use the probability out of this model as that first term there. However, if we were to just use, say, the track ID as input to the model, they would obviously not generalize beyond what you had already listened to. So rather than using the track, we chose to use features of the track, which could be, for instance, the artist, or maybe the style of the track, allowing for more generalization. But the best results came from using a feature called artist to vec, which you might guess or have heard of, or guess from the name, applies the idea of word to vec to artist co-occurrence in playlist and radio station data, giving us a vector representation of each artist so that can be passed into the user model. And by using this feature, we saw a 10% improvement in our ability to play the expected right song, which we thought was significant. And as an example on some of the real user data, we see on the left a word cloud representing a real user's musical tastes, which are, you can see, mainly country. And we were able to correctly select the Jake Owen version over the Katy Perry version here. And that is all I've got. I did want to say, if you're interested in learning about potential upcoming machine learning internship and co-op opportunities, and if you have any questions on slides later, please feel free to send me an email. And thank you for your time, and thanks for listening.
Thanks a lot, Isaac. So we have some time for questions.
I'll keep my eye on the Slack channel too, if anybody has any later.
Yes, that's true. So we have a couple of questions already. So one is, how do you deal with the ambiguity between entities and tags? Do you use any popularity metric for tags? That's a question by Sergio Ramos.
Any popular metric for what?
So how do you deal with the ambiguity between entities and tags, or do you use any popularity metric for tags?
I'm sorry, I just I might not have heard for tracks.
Do you want to for tags? Sergio, do you want to ask the question directly on?
Okay. No, just that you were talking about the ambiguity between entities and tags, like blues or some blues. You have the tag or you have the entity, and you say that you were using popularity to distinguish between ambiguities between artists and tracks, for example, so I wonder, how do you deal with this ambiguity between the tags and the entity, so the artists or the tracks?
But, oh, okay. So between different types of entities?
No, between entities and tags, for example, between an artist, for example, some blues, between blues, the concept of blues, the tag. So I'll be.
Oh, okay. Yeah. I mean, we found that just using the popularity data for those entities gave us a pretty strong performance. Sorry, let me think for 1 second. It was a while back. Oh yes. So at some point, there was a thresholding that would happen of the popularity from the entities against the probability from the language. But I don't know if I can right now discuss the details of that. Although I'll post later on Slack about it.
Okay.
Thank you.
Thank you, Isaac. I think there's another question, and we can finish the sit here. But please, you can still ask more questions in the Slack channel. So the question by Felix is, do the system you developed ask for clarification to the user? So is there like some sort of conversation aspect to this?
Yeah, we were mostly in the stage of prototyping this kind of functionality. So we were trying these kinds of things out, but it was an active area of research for us until it stopped. So that, yes, that's one thing that we did explore.
Thank you, Isaac. Let's thank our speakers, Isaac, again.